Slides have arrived.
All right.
And there we can see you too.
So, hello everyone. Just wanted to quickly introduce myself. Most people know me already. My name is Merlijn. I'm a researcher at IMEC and I teach at Ghent University. I'm also part of a number of open source organizations like the Ubuntu community. I'm going to talk about WebAssembly and specifically WebAssembly for Edge and IoT devices. This is a topic that's recently developing a lot, and we see a sudden interest from a lot of companies working with Edge and IoT devices in WebAssembly because it really can provide you a lot of value. First, I'm going to start to give a general introduction into what WebAssembly is and why there is, even though WebAssembly is already quite a mature technology, why there is a sudden interest in WebAssembly for IoT and Edge devices. And then I'm going to talk more about the specific use case of Edge devices. And finally, I'm going to end with a little bit of explanation about our current research on WebAssembly. So if you follow the Docker creator, a few years ago, he posted a post on Twitter that if WebAssembly and the WebAssembly system interface existed in 2008, they would have needed to create Docker. So why is it that WebAssembly seems to be such a magical technology? Well, WebAssembly itself, it's simply binary code. Very similar to, you can compile code for a physical CPU architecture like x86 or ARM. You can also compile code to a virtual CPU architecture, specifically WebAssembly. Because it's a virtual CPU architecture, it always needs to run inside of a runtime. These runtimes typically have been a browser or the Node.js runtime, but very recently we have seen a lot of Edge and IoT focused runtimes such as WebAssembly. These runtimes, either they have like just-in-time compilation, where it's literally the WebAssembly code is interpreted by the runtime during the running of the application, or you also have, to get even more performance out of it, you also have some ahead of time runtimes, which basically transpile your WebAssembly binary into a native binary before it runs so that you have near native performance. This is actually a virtual machine. Although most people would see it more in the context of the Java virtual machine. It's very similar to those things. So WebAssembly basically allows you to use any source language that supports WebAssembly, that supports compilation to WebAssembly. There's already a lot of support in a lot of languages like Python, Rust, Golang, C, C++, C#, because it is quite a mature technology that is used a lot for the web specifically. And then you basically just, instead of compiling to x86, you compile it to WebAssembly, and then you can run it inside of any WebAssembly runtime, be it a browser or a cloud native or an Edge runtime. So you have a lot of popular use cases already, where it's already used, Unity, AutoCAD, Photoshop, Google Earth, a lot of websites, a lot of IoT devices. And then in the IoT and Edge space, it's used a lot in, for example, video streaming applications. Netflix uses WebAssembly in order to have a single application that they can push to, I think they support about 2,000 different TV platforms. But they're all just, the application is just a WebAssembly runtime, and then The application on top of it is a WebAssembly application. And so the only thing they need to customize for the specific platform is the runtime. But the Netflix application itself, it's the same application on every device. So the thing that really makes WebAssembly interesting to edge devices is a change in how WebAssembly applications talk to the outside world. So for more technical people in the audience, this is in the context of system calls, syscalls. So what do I mean with outside? With outside, I mean everything that's not part of this WebAssembly virtual machine. Things like opening files, downloading files, opening TCP/IP sockets, doing multi-threading, contacting USB devices, or in the web browser, changing the HTML of your web page. The legacy system interface in the browser is the JavaScript API. I call it legacy because from an IoT standpoint, this is a legacy interface, but let's be real, this will remain the main WebAssembly system interface for browser applications. This is simply the same API that JavaScript code uses. WebAssembly, in order to download a file, it just runs JavaScript functions of the browser in order to download those files. And this was also the first iteration of WebAssembly on servers, uses the exact same API. The Node.js runtime, for example, uses the same JavaScript API, but it removes some browser-specific interfaces and it adds some server-specific interfaces. But there's a lot of issues with these APIs, specifically when you go look at Edge and IoT use cases, which is that the JavaScript API is quite inefficient. If, for example, you have a C or C++ application running inside of WebAssembly, well, then it needs to call JavaScript every single time it has I/O. Another issue is that the API is gigantic. The JavaScript API of browsers is incredibly large, and a lot of the functionality is not needed on Edge or IoT devices. And then finally, specifically when we look at the server APIs, they're not secure. By default, an application running inside of the Node.js runtime, it has access to almost the entire system. And even if you want to reduce some of the access, often the APIs themselves make it incredibly hard to actually reduce the access that an application has in the host system. So in order to solve these issues, the Bytecode Alliance and the W3C are currently developing the WebAssembly system interface. This is a new syscall interface built for speed, security, and cross-platform support. It is currently being standardized by the W3C WebAssembly system interface subgroup, of which IMEC is part of, and we are also working on this standard. And the tools and runtimes supporting the system interface are built by the Bytecode Alliance, which has a lot of browsers working on it, but also a lot of non-browser partners. Companies like Cloudflare and Fastly for their Edge offering, and Siemens for their IoT offering, and VMware for the virtualization and containerization angle. So this is why WebAssembly is suddenly becoming a very important technology, an important future technology for software packaging, software distribution, because of the system interface itself. And part of the WebAssembly system interface is the WebAssembly component model. This basically allows you to create pluggable WebAssembly modules. So if we take a look at how WebAssembly modules work normally, is that a WebAssembly module can import and export functions from other modules or from the host runtime, and for example, in order to call the JavaScript API. But there is no type checking. Basically, when a runtime connects two WebAssembly modules together, the only thing that's actually being checked is whether the function that the module calling something is the same function name, has the same function name as the module that's being called. But other than that, it could be that you're calling a function with completely different arguments, completely different return types. And this makes cross-platform support and cross-language support of connecting modules very difficult. So this is where the WebAssembly component model comes in. It's basically a wrapper around a regular WebAssembly module that adds typed interfaces. All the interfaces that a module imports and exports, the component part of the metadata also adds, okay, what are the types of these interfaces? What is the canonical API of these interfaces? So this gives you statically analyzable, capability-safe interfaces. When a runtime links multiple WebAssembly components or links a WebAssembly component to the own system call interfaces, the runtime itself can check if these interfaces are actually compatible. And there's a lot of tools, for example, to then generate language-specific hooks in order to call these interfaces from any language. You can just as easily generate Rust bindings, JavaScript bindings, C, C++, Java bindings from the exact same description of these interfaces. And there is a canonical API with strict compatibility guarantees that explains how these interfaces are then translated into actual bits and bytes. These at the right here, you see how such an interface is described. Interfaces are defined in an interface description language called WIT, which is a cross-platform, cross-language description of what an interface actually is. And the WebAssembly system interface, the first preview of the system interface, did not actually use this component model, but the second iteration of this system interface has switched to the component model and allows you to have a lot of guarantees about the compatibility of components. This also allows a lot of language interoperability. It allows you to link a component written in JavaScript, one in Golang, one in Rust. It allows you to just link them together into a single component and still have guarantees that all the types will be compatible. And so in this sense, you can see WebAssembly components as like cross-platform libraries. You can write different components in different languages and then link them together into a single WebAssembly component. Between these components, when multiple components use the same module, this module is duplicated. There is shared nothing methods between components in order to ensure these security guarantees. Because multiple components can, for example, have multiple supply chains, can be written by multiple different companies in order to ensure the stability and the security of the entire application. Communication between these components is seen as crossing a security boundary, and because of that, there is a default of shared nothing between components. Inside of a component, they're shared everything. So you can still link libraries together into a single WebAssembly component, but then all libraries inside of this component share the same shared library. And so the combination of WebAssembly system interface and WebAssembly components are what is turning WebAssembly into the new containers. And from our perspective, we think that WebAssembly components and the WebAssembly system interface will result in the first time that large cloud providers will move away from virtual machines in order to separate tenants. So I'm not sure if you know this, but if you go and look inside of how Amazon's Lambda serverless offering works, even though customers are actually just writing a single function, customers between each other are still separated with virtual machines. So if you are running a single function inside of AWS Lambda, AWS will provision a virtual machine for that single function, then create a container inside of that virtual machine, and then inside of that container, it will create a function. And then if another customer also runs another function, it will create a new virtual machine, a new container, and then inside of that container, a new function. This is the reason why AWS Lambda can be prohibitively expensive. We are actually seeing a lot of big cloud providers and edge providers create incredibly cost competitive solutions using WebAssembly, because instead of having to spin up a new virtual machine for each customer, they can run all customers inside of the same virtual machine, the same container, but as different isolates, where each isolate is a different customer. The reason why we see customers like Cloudflare and Fastly, for example, and companies like Cloudflare and Fastly, they are already doing this. And that is why their compute is so much cheaper than the compute of AWS Lambda, for example. And the reason why they are confident in doing this is because this stuff is using the exact same isolation techniques that are protecting, for example, all your banking, all your web banking stuff. The same technology that is making sure that if you have multiple tabs open in your browser, one with your banking information, one with whatever website or YouTube, the same technology that is isolating these tabs in your browser is isolating customers inside of Fastly and Cloudflare data centers. And so since there is a lot of research already built in ensuring that these sandboxes are incredibly tight, this is what allows these companies to actually switch from isolating customers with virtual machines to isolating customers with something that has a lot less overhead. As I said, the WebAssembly system interface and the component model are being standardized by the W3C as part of the WebAssembly system interface subgroup, and the runtimes are being developed by the Bytecode Alliance. The runtimes, there are two main runtimes that the Bytecode Alliance is developing. Wasmtime, which is a runtime focused on cloud and edge use cases, and WAMR, the WebAssembly micro runtime, which is focused on edge and IoT devices. And when we look at IoT devices, the size of IoT devices that this can run on, it's crazy. WAMR, for example, the WebAssembly micro runtime, uses about 50 kilobytes of overhead, of memory overhead, in order to run itself. So using WAMR, using WebAssembly on a microcontroller with 265 kilobytes of RAM is something that is completely attainable. And so for the first time ever, it is possible to have container-like things on a microcontroller. And so in terms of when we're talking about, for example, supply chain attacks and things like that, this suddenly allows you to actually have much more robust protection against supply chain attacks by isolating different components of the software that is running on a microcontroller. Back to the community, I can definitely, if you're interested in using these runtimes or in developing standards, I can definitely recommend to go to the Bytecode Alliance Zulip chat, because a lot of the developers and people who create the standards are there and are happy to discuss these things with you. One of the questions that people often ask when I give a presentation like this is, okay, but what is the difference between WebAssembly and the Java runtime? And the answer is that there are a lot of similarities in both design and use cases. When you would go to the Java developers when they were initially developing Java and talked to them about, okay, what is your 50-year goal with Java? A lot of their goals seem to be very, very similar and very aligned with the goals of WebAssembly. But in a sense, WebAssembly learned from the mistakes that Java created. Both WebAssembly and Java have this idea of write once, run anywhere. This idea of architecture independent bytecode. Running this architecture independent bytecode on microcontrollers. For example, Johnson Control heat pumps, they're using the JVM on their microcontrollers, or using JVM in order to have much more advanced browser applications like the old vSphere web UI. But ultimately, the JVM failed in most of these fields. Ultimately, the JVM currently is just used as a single vendor runtime for a single family of languages. Java, Scala, and a couple of other languages in that family. This is in order to not have the same fate for WebAssembly. WebAssembly made a couple of different choices where JVM basically learning from JVM's mistakes. The first one is that WebAssembly was built as a compilation target for all languages. The focus was on a standardized compilation target that is completely language independent. On the flip side, JVM is much too reliant on a single vendor, Oracle, and focused on a single language family. It's only very recently that the JVM has actually been open sourced completely. JVM is also way too opinionated about which languages run inside of it. For example, the JVM requires that languages use classes. It requires that languages use the garbage collector of the runtime. Also, JVM is not sandboxed by default. WebAssembly is sandboxed by default. And this not only has security implications, but this also has compatibility and cross-platform implications. You know, the typical snide remark about Java is write once, debug everywhere. Because if you write Java code on Windows, it will probably not run on Linux, even though write once, run anywhere is the mantra of Java. This is because JVM applications have way too much access to the underlying operating systems, and as a result, they constantly use underlying operating system functionality that is not cross-platform. And also, it is very, very difficult to run it from a security standpoint. The JVM basically assumes that all code running inside of the JVM is trusted. Having multi-tenant applications inside of a single JVM requires you to write the multi-tenant functionality as part of your application instead of being able to rely on the multi-tenant functionality of the runtime itself. And then finally, software delivery is baked into WebAssembly. Things like streamability of applications. Your browser can start running an application way before it receives the last bytes of that application. From the moment it receives the first bytes of that application, it can start running it. And then secondly, hot plugging. The WebAssembly hot plugging is by default built into the runtime. You can easily swap in and out certain components of your application at runtime, and everything will keep running. While the JVM is way, way too focused on those traditional monolithic applications of a single static monolithic application that's already on the user's machine when it runs. So, WebAssembly on Edge and IoT devices. Why is this seeing so much interest? I've shamelessly stolen the slide from Bosch here because Bosch is a creator of a lot of chips in automotive systems. And this is their explanation of the complexity issue that WebAssembly can solve for them. automotive software is incredibly complex. Most cars or all cars have at least dozens of interoperating ECUs. A lot of electric cars can have up to 300 interoperating ECUs. So that's separate computers inside of a car, 300 separate computers. And there's a lot of tight coupling between the software and the underlying hardware. There's a lot of regulatory requirements, a lot of cost constraints, and a lot of requirements for compatibility with different vendors and over time spans of up to 50 years. Updating software in such an ecosystem is an incredibly slow process. Upgrading hardware in such an ecosystem is almost impossible. The idea is that WebAssembly can act as a narrow waist of automotive software. WebAssembly is basically the bridge between the hardware and the software. It allows developers to use the latest tools and compilers to build their applications using the latest languages and just compile them to WebAssembly. And then the WebAssembly runtime basically translates everything to the actual hardware that it's running on. So let's take a deeper look into the advantages of WebAssembly and WebAssembly system interface for embedded. The first one is binary device portability across instruction architectures and platforms. So the same application can run on RISC-V, can run on ARM, can run on Intel devices, which allows a lot more flexibility in changing the underlying hardware. It also allows you to support much more programming languages. If you're in the embedded space, most of your programming language choices are just a single choice. You have to use C because that's the only programming language that the underlying hardware supports, that you have a compiler for that specific hardware. And it also allows you, WebAssembly also allows you language interoperability. Use multiple different programming languages in the same application on the same hardware. Especially interesting is the idea of forward compatibility with newer application toolchains over the time span of multiple decades. And then finally, it allows you secure and sandboxed execution of software in platforms where other solutions like containers simply don't fit, while still ensuring support for existing WebAssembly and for existing software that wasn't compiled for WebAssembly. You can still compile it to WebAssembly to run it on this platform. You don't need to switch programming languages. You don't need to rewrite all your software in Java before you can start using this. You can just keep using your existing applications. And then also, very, very important, near native efficiency in execution and compilation. Interestingly, some of the benchmarks that we're doing, the WebAssembly micro runtime actually has better performance than native code because of the optimization opportunities in WebAssembly binaries. The runtime is able to execute these programs a little bit faster than native speed. But for most runtimes and for most use cases, you see like around a 10% slowdown. So what we are working on in IDLab Discover is working on future advantages of using WebAssembly on microcontrollers, and that's the idea of secure drivers. Drivers that only access what they actually need. Typically, a driver has complete access to the entire operating system because it's running unprotected in layer 0. This makes it difficult to defend against supply chain attacks in the supply chain of the drivers. And this makes it very, very difficult to ensure incredibly high reliability and robustness. Because when your driver crashes, your entire kernel crashes and you have nothing anymore. So with WebAssembly, you can actually defend against supply chain attacks by sandboxing the drivers. and we can get a much higher reliability and robustness by sandboxing components. And if a certain driver crashes, the runtime just restarts the driver and the system can keep running. And then secondly, this also allows you to create portable drivers that work on any architecture, any platform, support newer hardware on older platforms, and basically write a driver once, run it anywhere. More specifically, our research, the first track of our research is connecting WebAssembly applications to hardware via I2C, USB, and other interfaces. And so this is the goal, basically, of having a runtime that just has a generic USB interface, and then the drivers themselves can run as WebAssembly components that then plug into other components and are hot pluggable. And so if you have a car that's 30 years old and you need to update the camera used by the driverless system, for example, and the old cameras are not produced anymore, that you can very easily just plug in a new camera, the new driver loads as a WebAssembly application, and your system can keep on running. So this allows you much easier support of new hardware on older systems. Smart Factory is an extreme example of this, where a lot of Smart Factory machines have a lifetime of up to 50 years. You can get a lot more secure drivers and a lot more portable drivers. Specifically, we're building a few WebAssembly system interface proposals and then implementations of a lot of these runtimes. The I2C WebAssembly system interface proposal is something that we're building in order to connect WebAssembly applications to low-level sensors, USB in order to connect WebAssembly applications to USB devices. And then we also have a couple of other proposals which are currently on hold. For example, the GPIO proposal. All these proposals are standard proposals with standard compatible implementations for all these interfaces, so that we are sure that companies like Siemens writing their applications using these standards, in 30 years, they will still be able to use the latest tool chains because they are all compatible with these standards. The second thing we're doing with WebAssembly is basically shrinking Kubernetes. There's a lot of companies that are very happy with the cloud native developer experience, with the Kubernetes experience for cloud applications. But then a lot of these companies have both a cloud part of their application and an edge part of their application. And then whereas for the cloud part, they can use the latest tools, they can use CI/CD, very advanced sandboxing and things like that. For the edge part, they are basically stuck with an ecosystem that resembles much more what the cloud was 15, 20 years ago than what the cloud is today. So they are basically asking, why can't we get Kubernetes or something that's compatible with Kubernetes? Why can't we get this on edge devices? And the reason is that Kubernetes is currently a bad fit for edge devices. Kubernetes is a hungry hippo that really likes to eat your resources. For example, the kubelet itself uses a lot of RAM by itself. We're working on a project, a re-implementation of the Kubernetes kubelet that uses about 10% of the actual resources of the default kubelet. Same with container runtimes, use a lot of resources, the API server, but specifically where we're using WebAssembly is in order to reduce the resource usage of operators. So Kubernetes operators are plugins into the Kubernetes control plane. Like Thomas talked about, they're creating an operator in order to manage Obelisk in Kubernetes. You also have operators that you can use to manage MySQL databases, to manage Kafka. Operators are the default plugin for Kubernetes clusters. They're a great way to extend Kubernetes clusters with extra functionality, but they use a lot of resources. And that's because operators are written as long-running processes. Each operator is its own web server that is constantly listening for changes. And when there is a change, it processes the change. And when the processing ends, it keeps on running because this web server keeps on running. It keeps on using RAM. It keeps on using resources. And most of them are also written in Golang, and Golang is also a hungry hippo that really likes to eat your RAM. They're running in containers with a lot of overhead. So our solution for this problem is to run operators in WebAssembly. The system that we built uses a parent operator. The parent operator is basically the WebAssembly runtime. And the WebAssembly runtime is the only thing that keeps on running and keeps watching these Kubernetes resources. The parent operator, that's the system that listens to changes. And then when a new change comes in, it starts a child operator simply to process that change. And then when the change is processed, then it shuts down the child operator again. This has a lot of advantages. One of the advantages is that simply by running these operators inside of WebAssembly, they are already using 68% less RAM. This is partly due because a lot of the functionality is as part of the runtime, so it doesn't have to be duplicated for each running operator. And another part of this advantage is because you're not having the overhead of a complete Linux user space in a Docker container for each operator that you're running. You only have the application binary. Then given that we are using WebAssembly, we can do a lot of cool stuff with this, like unloading operators when they're idle and reloading them when there's new events. Because in contrast to a Docker container, a WebAssembly container can start up in a millisecond. This is millisecond latency for startup of a single application. This is why WebAssembly is so critical for having actual cost-effective serverless platforms, because there's almost no overhead to actually starting a WebAssembly application. And so when we then, instead of just running these operators as long-running processes inside of WebAssembly, when we actually also unload them, in a worst case, we see that we use an additional 50% less RAM. However, it is at the cost of latency, because there is a latency associated with starting operators. So there is an additional cost of latency. This is why our current research is looking into, for example, using machine learning in order to predict when operators will have to be reloaded and be able to reload them beforehand in order to have better latency, better reactiveness into this. The other track of our current research on this platform is to actually go to the Kubernetes ecosystem, show them what we have, and try to actually get some broader buy-in from the Kubernetes ecosystem itself. Because every single time we interact with people inside of the Kubernetes ecosystem about this platform, they're like, oh my God, this is amazing. We really need this inside of Kubernetes. But the issue is that the current discussions we've had have not actually led to a broader effort where other companies or other research organizations join in. So we're currently looking at how to actually get a broader effort into this platform so that it hopefully also can become one of the standard ways to build operators. So this was it for this presentation. If you have any questions about using WebAssembly, especially WebAssembly for IoT and Edge use cases, please send me an email. We're always happy to collaborate on these topics. And if you have any questions right now, I'm happy to answer them.
So when you said that the WebAssembly can start on when an event occurs, what kind of events would this be? Like, for example, is this a dbus call that happens? Is this a socket call that happens, API somewhere?
So for WebAssembly runtimes in general, all of the ones you described, this works. Most of the runtimes support starting WebAssembly functions when you have HTTP calls, when you have internal socket calls, things like that. For our platform specifically, this operator platform, this is based on calls from the Kubernetes API server. So basically an operator, it subscribes to certain events in the Kubernetes API server, and then it basically gives an HTTP callback URL to the API server. Like if this event happens, then send an HTTP request to this callback URL. The callback URL in this system is the WebAssembly runtime. And then based on what callbacks it gets, it will start these operators. And so this is the default way for operators to interact with the Kubernetes API server. So basically anything that an operator is currently doing with the API server, all that is already supported in this platform. One of the difficulties is that some of the operators, for example, you have operators to manage Kafka. They also have additional calls to Kafka and also use like certain event-based APIs in order to contact Kafka. Those are not yet supported in our platform.
So when you said that you can use WASM as a way to transpile to AOT, would that also be possible for languages that currently do not support AOT? You transpile them to AOT states?
Yes, that's a very good question, and the answer is yes. Any language that compiles to WebAssembly can run on IoT devices, can run on anything. Basically, runtimes, WebAssembly is basically the default compatibility layer between the underlying platform and the language. So if your language, so there's basically two things that need to be that need to be compatible. First of all, your language needs to be able to be compiled to WebAssembly, and today most languages can be compiled to WebAssembly. And then the second thing is that the IoT device needs to support one of the WebAssembly runtimes. And this will probably be the WAMR, the WebAssembly macro runtime, which already supports most common IoT platforms. Like from a very almost IoT supercomputers like a Raspberry Pi to like incredibly low ESP32 processors, for example. A lot of the tiny ARM Cortex processors, they're all supported by the WebAssembly micro runtime.
Some more questions, if you don't mind. So when we're talking about the cloud specifically and running these WASM applications in the cloud, how would you currently go about deploying these? Like if you say Kubernetes as an underlying system to deploy these with Docker containers, would you run the runtime in such a Docker container, or is there a way already to replace the Docker container itself with a runtime?
Yeah, so if you want to do it in the Kubernetes ecosystem, there's basically specific type of kubelets that have a single runtime on every host. And then the WebAssembly applications run inside of a single Docker container, inside of a single runtime for each host. And then if you run 10 WebAssembly applications on a single host, then you will only have one container for the runtime, and then 10 will run inside of this runtime. If you want to go a little bit further away from Kubernetes, you also have very interesting technologies like OpenCloud. OpenCloud is basically a Kubernetes-like orchestrator specifically built for WebAssembly, which has even less overhead and a lot better performance than Kubernetes itself. In terms of the images, what images do you give to Kubernetes? Often you have two possibilities. Either you use an OCI image, because WebAssembly recently, there's a standard in order to have OCI images with WebAssembly applications, or you just use a standard WebAssembly module or WebAssembly component that you then give to the orchestrator, and then the orchestrator runs those in the runtime.
Okay, last question. So if we're talking, for example, the operating system like Ubuntu Core using snaps, the nature of the snap is that it's already in its own little sandbox. So in these use cases, you still have to include the runtime within each of those snaps. You foresee any progress being made where the one runtime can just be underlying of all these snaps and can use the layer below it?
So, first of all, from a technical standpoint, I think the easiest way would be to create a content snap for the WebAssembly runtime. That would mean that on disk, the runtime is only once on disk, but then you would still have the issue of multiple snaps still use multiple instances of the same runtime. I think an easy way to go to solve this problem, low-hanging fruit, is to just have a single snap with a WebAssembly runtime, and then have a second orchestrator put all your WebAssembly applications inside of the single runtime in a single snap. So that you only have a single instance of your WebAssembly runtime itself running. But on the long term, I think Linux distributions should take a serious look at WebAssembly, and especially Ubuntu Core, for example, should take a serious look at WebAssembly to make WebAssembly a first-class citizen of those platforms. I have connections with Canonical. I am currently in talks with them about things like that, but there is currently nothing concrete about it. There's currently nothing happening, and I have no idea if something like this will happen in the future. But I think they should do it. Otherwise, they will be replaced by operating systems that do have it as a core software distribution concept.
Small question for me. What would be, how do you see the level of maturity of this now? I mean, you indicated already, but is it really set for production, or is it still to be further maturing?
So, in terms of maturity, one of the things I can say is that there are already millions of microcontrollers out there in cars that are running today that are using WebAssembly and the WebAssembly system interface.
Specific brand, or?
I'm not allowed to divulge that information.
It starts with a T and ends with an A.
There's a couple of European car manufacturers that are already using it in their cars. I think for the moment it is production ready and it is possible to use it. However, it is production ready in the sense that when you have a team of developers, an in-house team of developers that want to take the current technologies and change it a little bit in order to turn it into a product, then it works. And so for a lot of these companies like Siemens, like Bosch, a lot of these auto manufacturers, they are used to doing things themselves. And so what they're doing is they're taking the current runtimes, they basically have an internal fork, where they change it a little bit in order to make it fit their use case, and then they use that in production. I would say if you're a company that just wants a product that works off the shelf, WebAssembly for IoT is not there yet. WebAssembly for edge computing is completely there. Cloudflare, Fastly, and Fermion, and OpenCloud, for example, are four companies who have productized offerings that are no frills, everything just works. It's amazing what kind of experience, user experience, developer experience they can offer with WebAssembly. And then WebAssembly in browsers and WebAssembly on IoT devices like TVs. Well, that's been there, that's been production ready for, like, I would say, maybe past 4 or 5 years or something.
Okay.
I also have a question. Earlier you were showing the differences between using WebAssembly and what Amazon already has in terms of container and virtual machine and container. And I'm curious, I'm wondering, are there security related differences between these two types of developing a function or something? Are there major differences in terms of security?
So in terms of security, the major difference is that when you're using virtual machines, you can rely on basically hardware isolation between virtual machines. Whereas WebAssembly itself, the V8 engine, it uses some hardware isolation techniques, but it doesn't use as much as like proper virtual machines use. However, I would say that in practice, a lot of the cloud providers who are already using V8 and WebAssembly in order to isolate customers, in practice, there are very little security implications for you as a user for switching to a provider that uses V8 to isolate you instead of a provider that uses virtual machines to isolate you. I think the customers would need to have incredibly high security requirements in order to actually require using virtual machine isolation instead of V8 isolation. Because of the simple reason that most companies already completely rely on V8 in order to isolate untrusted code in their web browsers. Like, if you're using Google Chrome in your company and you have a tab open with your accounting software and then another tab with Google or YouTube, then you're already isolating multiple tenants and already relying on that in order to protect your financial information. If it's good enough in order to protect your banking website and your accounting software, why wouldn't it be good enough in order to protect your servers?
Thank you.